Hello, ma'am.
Good evening, sir.
Yes, ma'am. Good
Good
evening,
evening,
ma'am.
sir.
Good evening, Ajay.
Good
Ma'am.
evening, sir.
Yeah, ma'am. Make me a host, ma'am. Good evening.
Yeah, sir, I did, sir. You can continue, sir.
Okay. Good evening to all. All are there. Yeah.
Good evening,
All
sir.
right. So, yeah, good evening. Today, we are going to finish this chapter. Almost we have done. We have done the derivation also last class. If you remember, to calculate the energy of activation at two different temperature. We have learned the derivation. I will write the equation, then you will remember log K2 by K1 is equal to EA by 2.303 R T2 minus T1 divided by T1 T2. We derived this equation. That is to calculate the energy of activation at two different temperature. All right. Now, concept of activation energy, all that we learned in the last class, will continue this reaction also. I told you, did I teach you the reaction mechanism for hydrogen iodide formation? Okay, you won't remember. That's fine. The same graph we will simplify. This is potential energy. This is the progress of the reaction or reaction coordinate. It is called as reaction coordinate. Now, every reactant molecule will possess minimum amount of energy. That's called as normal energy. Here they are represented as EP. We will write it as EN, normal energy. When the molecules collide with normal energy, it will not lead to the formation of the product. Now, we all know from this reaction that is hydrogen and iodine gives you 2HI. This is the reaction. But this reaction does not give you the mechanism. So chemical kinetics also teaches us mechanism. So if I take the reactants H2 plus I2, these molecules, when they collide, it will not lead to the formation of the product. It will not lead to the formation of the product. Why? Because the energy associated with these molecules are less. Therefore, what happens is these molecules will gain an energy called as activation energy. This energy, the molecule which gains, is called as activation energy, EA. Now, once the molecule gains the activation energy, what happens is this hydrogen and iodine will react to form an activated complex. An activated complex, see, H2 and I2. This activated complex is also called as intermediate compound. Activated complex or intermediate compound. This is activated complex here. This activated complex will have high energy. Now, since they have high energy, they are less stable. They will decompose to form the product. Now, when I say they decompose to form the product, here you can see the products are formed. 2HI. So this energy is called as threshold energy. What is this threshold energy? Threshold energy is the product of normal energy and activation energy. A molecule, normal molecules, has to gain the activation energy so that it acquires threshold energy. So molecules, whichever molecules have threshold energy, when they collide, it leads to the formation of the product. You can see this is the energy with respect to the products. So the energy with respect to the product is less compared to the energy with respect to the reactants. This we have marked it as delta H. Here a delta E, energy is delta E. This is the energy associated with the reactants, and this is the energy associated with the product. So a molecule, if they have to undergo effective collision or fruitful collision, it has to overcome two barriers. One is called as energy barrier. So that means the molecule should gain what? Threshold energy barrier. The second one is called as orientation barrier. We have learned orientation barrier also in the last class with an example of hydrogen, nitric oxide, nitrogen dioxide reacting with each other to form the product, nitrogen tetroxide. We learned the orientation of the molecules. Anyways, we will learn with orientation of the molecules with one more example, what is given in the textbook. We will learn that. The next theory, what we learned is called as collision theory. What we learned is called as collision theory. In your syllabus for 12th standard, you have only collision theory. You do not have transition state theory, but we will learn. Did you understand what is collision theory, students?
Yes, sir.
Yes. Now, transition state theory. According to transition state theory, the activated complex is supposed to be in equilibrium with the reactant molecules. Once the transition state is formed, it can either return to its initial reactants or proceed to the formation of the product. So this transition state theory states that the activated complex which is formed, it should be in equilibrium with the reactants. Molecules. Once the transition state is formed, it can either return to its initial reactant or proceed to form the product. Assuming that once formed the transition state proceed to products, we can say that rate is proportional to the concentration of the transition state. So assuming if a transition state is formed, then the rate of the reaction is proportional to the concentration of the concentration of the transition state. Mathematically, rate is directly proportional to transition state, or rate is equal to constant into a transition state. Now, Arrhenius equation we learned, K is equal to A into e to the power minus EA by RT. All this we learned. And we learned the derivation also. I taught you the derivation of this equation also in the last class. Now we will learn some questions. Before we learn some questions, we have to understand the proper orientation, which your textbook is given. I'll use this space. All right, for proper orientation, we can write the equation, Arrhenius equation, K is equal to A into e to the power minus EA by RT. This equation looks similar to this. Rate is equal to P into ZAB into e to the power minus EA by RT. Rate of the reaction is equal to Z into P into ZAB e to the power minus EA by RT. What is this Z? Z is called as collision frequency. Collision frequency. Collision frequency means number of collisions per second per unit volume. This is what's that? Z. It's represented by letter Z. A and B stands for molecules. A and B stands for molecules. When I say A and B stands for molecules, A is an atom and B is an atom, or A is a molecule and B is a molecule. All right. Now, what is this P? P is nothing but the orientation factor or frequency factor. Orientation factor or frequency factor. So this equation you should remember, rate is equal to Z into P is not Z, P into ZAB e to the power minus EA by RT. All right, now just observe. Do you remember that in your 11th, not 11th standard, in your school or in college, they would have taught you SN1, SN2 mechanism? Have you heard of that? Have you learned SN1, SN2 mechanism, organic chemistry?
Yes, sir.
Yes. Now, what do you mean by SN2 mechanism? What does SN2 stands for? SN2 mechanism stands for nucleophilic substitution bimolecular reaction. So SN2 reaction is predominantly undergone by primary alkyl halides. Primary alkyl halides. Now, example for a primary alkyl halide, we will take methyl bromide. We'll take methyl bromide. This methyl bromide, when allowed to react with a nucleophile, OH minus, there is two possibilities. When we say there is two possibilities, one is improper orientation. One is improper orientation. The other one is called as proper orientation. Now, when I say improper orientation, This improper orientation will not lead to the formation of the product. When I say improper orientation, now just observe, bromine is negative and the nucleophile is also having negative charge. So when OH minus attacks bromine, what happens here? Repulsion will take place. When the OH minus will be repelled by bromine, therefore what happens? No reaction will take place. No reaction. But if we say, if we write like this, the methyl bromide, if I write like this, H, and this is bromine, and the nucleophile is attacking in the opposite direction, opposite direction of bromine, there is no repulsion. So what happens? The OH will start forming the bond with bromine. Likewise, this is OH. Likewise, the bond between carbon and bromine starts breaking. See the straight line I've written here. Here I'm writing the broken line. So that means the bond is formed between carbon and OH. Likewise, the bond is broken between carbon and bromine. This is called as transition state. It's called as transition state. Once the bond is completely formed between carbon and OH group, so what happens? We get an alcohol, methyl alcohol, and bromine gets eliminated as the byproduct. So the product is obtained. So when there is a proper orientation, then it leads to the formation of the product. Leads to the formation of the product. So in collusion theory, both the steric factor, this orientation is called as steric factor otherwise, steric factor and the energy barrier together determine the criteria of effective collision. Effective collision. So in collision theory, there are two criteria which decides the effective collision. What's that? One is steric factor. It's otherwise called as orientation factor. The other one is called as energy barrier or energy factor. The energy factor has to be overcome, and also the molecules has to be properly oriented. Only then, when the molecules collide, it will lead to the formation of the product. Did you follow this?
Yes, sir.
Others? Others? Nobody else is there? What happened? Others, are you following?
Yes, sir. Following.
Yeah. Please answer me. I'll be happy. Okay. Now, today we'll be finishing with this chapter. We'll be starting with the next chapter in the next class, coordination compounds or coordination chemistry. A few questions I've typed. We'll work on those questions and then we will do some more questions on this chapter. Right. So, can you see the screen?
Yes, sir.
Yeah. Okay.
Yes, sir.
Yeah. Mm-hmm. Now we will learn some of the questions here. Was the first question. Which of the following statement about the catalyst is true? Okay, one more point I should tell you. I forgot to effect of catalyst. That is also an important question for your 12th standard. I forgot to tell you. Only now I'm remembering based on the question I'm remembering. I will tell you that effect of catalyst on the rate of a reaction. Now I will erase this part and teach you. One minute. Just give me a minute. I'll erase this and teach you the effect of catalyst on the rate of a reaction. You know what is a catalyst? Define a catalyst. Let's see. What is a catalyst? How do you define a catalyst? Anyone? Catalyst is a chemical substance which alters the rate of a reaction. Or catalyst is a chemical substance which increases the rate of a reaction, or catalyst is a chemical substance which speedens the rate of a reaction, which fastens the rate of a reaction. Those are called as catalysts, right? Chemical substance which increases the speed of a reaction will be called as a catalyst. Now, the effect of catalyst on the rate of a reaction. This is an important question for 12th standard. Effect of catalyst on rate of a reaction. Now, can anyone read what I'm writing now? What is this molecule KClO3 called as? What is KClO3 called as? This KClO3 is called as potassium chlorate, CHLORATE, potassium chlorate. This potassium chlorate, when you heat, it decomposes to form potassium chloride liberating oxygen. So one of the method of preparing oxygen is this. Take potassium chlorate, heat it. Okay, so you get this potassium chloride will decompose to give potassium chloride, which is a solid, which will remain in the container, and oxygen gas gets liberated. So this is one of the method of preparing pure oxygen. Now this reaction does not happen at low temperature. When I said this reaction does not happen at low temperature, what do you mean by it? We have to heat it to a very, very high temperature. Now this is potential energy and this is reaction coordinate. If I have a reactant here, now we have to heat it to a very high temperature. Now we have to heat it to a very high temperature, and only then what happens? It will decompose to give you the product. It will decompose to give you the product. This is called as the energy of activation for an uncatalyzed reaction. Uncatalyzed reaction. See here in this reaction, I'm not used a catalyst. So when we don't use a catalyst, the energy required for this reaction to take place is very high. The energy required for this reaction to take place is very high. Now the same reaction, if you perform in the presence of a catalyst, MnO2, manganese dioxide, same reaction we're performing in the presence of manganese dioxide. At 40 degrees, 45 degrees Celsius, it will decompose. Meaning the same reactants in the presence of a catalyst, it takes the different reaction path. It takes the different reaction path. This dotted line, what I'm drawing, is showing you the reaction in the presence of the catalyst. Now you can see in the presence of the catalyst, the energy of activation for decomposition is very less. To attain this energy, the time required will be very less. Therefore, what happens? The rate of reaction becomes faster. You understand what I'm telling? So whenever we use a catalyst, what happens is the first point, whenever we use a catalyst, reaction takes a different path. Reaction takes a different path, the first point. Second point is whenever we use a catalyst, all right, energy of activation is decreased. Energy of activation is decreased. See here, the amount of energy required with the catalyst is what? Very less. Therefore, what happens? The speed of the reaction increases in the presence of the catalyst. This is energy of activation for what reaction? A catalyzed reaction. Catalyzed reaction. That means when we use the catalyst, the reaction takes in a different direction, and also by decreasing what? The energy of activation. Therefore, the reaction becomes faster. All right. So 2 points you should remember. When we use a catalyst, one is it takes a different path. Second one, catalyst decreases the energy of activation. When the catalyst decreases the energy of activation, the speed of the reaction increases. Do you understand? Effect of catalyst on the rate of a reaction, they can ask you 2 marks. So you should write this energy profile diagram and explain whenever the catalyst used, the reaction takes place in a different path and the energy of activation is decreased by the catalyst. Therefore, the rate of reaction increases. Followed?
Yes, sir.
Others followed?
Yes,
So
sir.
we'll
Following.
start with, yeah, good. Yeah. We will do some questions, the regular questions we will learn, and then we'll see what can be done. Which of the following statements about the catalyst is true? A catalyst makes the reaction feasible by making delta G more negative. We are not talking about the free energy concept here in this chapter. So this is ruled out. A catalyst makes equilibrium constant more favorable for forward reaction. No, a catalyst will make equilibrium constant more favorable for both forward and backward reaction. A catalyst accelerates, this also is wrong, accelerate the rate of reaction by bringing down the activation energy. Yes or no? Just now I taught you. Whenever I taught that. Now, whenever we are using a catalyst in a reaction, the reaction takes place in the different path, and also what happens, the energy of activation decreases, I told you. So a catalyst always increases the rate of the reaction. This is also right, because in modern days in NCRT, we do see in the olden days, we had two types of catalyst. One, they called it as a positive catalyst. The other one, they called it as a negative catalyst. This positive catalyst increases the speed, increases the rate. The negative catalyst decreases the rate. In modern days, they don't call it as a negative catalyst. They call it as an inhibitor. They call it as an inhibitor. So whenever we use a catalyst, it means it should increase the rate of reaction. So this question, this option was based on the older syllabus. So you should remember, whenever we use the term catalyst, it always increases the rate of reaction. So the negative catalyst in modern days, it is called as inhibitors, which slows down the reaction, is called as an inhibitor. Right. So here, since I know the answer, and since I know this is wrong, this is the wrong statement in the modern days, we know that the right option for this particular question is a catalyst all accelerate, increases the rate of reaction by bringing down the energy of activation. Followed? The answer is B, C for this. The next question. When a catalyst is used in the equilibrium process, when the catalyst is used in an equilibrium process, it increases the rate of forward reaction, it decreases the rate of backward reaction, it decreases activation energy for both forward and backward process, it fastens the attainment of equilibrium by lowering the activation energy. So whenever we use a catalyst in an equilibrium process, it's a reversible reaction. When I was talking about a catalyst, I took the example KClO3. It's only a forward reaction, not a backward reaction. So there is no equilibrium for that reaction. So whenever we use a catalyst for a reversible reaction, wherein there is an equilibrium, so catalyst will help in the attainment of equilibrium by lowering the activation energy. So the answer is option D. Option D. The next question. The rate constant for first order reaction at 300 degrees Celsius, for which EA is 35 kilocalories per mole. The temperature they have given is 300 degrees Celsius. That is 573 Kelvin, right? And they've given you the energy of activation to be 35 kilocalories per mole. And frequency constant, they have given frequency constant, that is A, Arrhenius factor is called as frequency constant, and they've given it as 1.45 into 10 to the power 11 per second. And they're asking you to calculate the rate constant. So how do we calculate the rate constant? We know that K is equal to A into e to the power minus EA by RT. So if we take log K, that will be equal to log A minus of EA by RT. Since we're talking about log LOG, it will be 2.303 RT. So we can write log K is equal to log of A. What is A? 1.45 into 10 to the power minus 11. Minus of energy of activation, they've given 35 kilocalories. Now, kilocalories, you have to take it in calories. Calories divided by 2.303. A was the energy, was it R value? R value is 8.314 into temperature is 573. So on simplification, we will get log K to be minus 2.1. So K will be anti-log of minus 2.1. So for negative value, there is no anti-log. So you have to ignore this minus sign. So you have to check the anti-log of 2.1. The anti-log of 2.1 is 7.94 into 10 to the power minus 3 per second. So anti-log of 2.1 is 7.94 into 10 to the power minus 3. Hence, the answer for this question is option D. So you should be in a position to learn from the physics teacher or the mathematics teacher how to find the log, anti-log. All right. In the competitive exam, they will not give you the log books also. So you should know, you just ask them how to find the log and anti-log, or the any shortcut methods to find the anti-log with them. You can talk to the physics teachers, they will help you out. All right. So I just told you the procedure of working this problem. So only the mathematics part of it you have to take care. All right. The next question. For a reaction, activation energy EA is equal to 0. For a reaction, activation energy EA is equal to 0. And the rate constant at 200 Kelvin is 1.6 into 10 to the power 6 per second. The rate constant at 400 Kelvin will be, now we know the equation log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 divided by T1, T2. Now, since EA is 0, can I say log K2 by K1 is equal to 0? Can we say? Yes or no?
Yes, sir.
What will
Yes,
we
sir.
see? If I bring log to the other side, what will happen? Anti-log of 0. Log 1 is 0. That means anti-log of 0 should be what? 1. Correct. Log 1 is 0. So anti-log of 0 should be what? Opposite of that, it should be 1. So we can write K2 by K1 is equal to 1. Now they've given you K1. What is that K1 they've given you? K1, maybe I'll write like this. K2 divided by K1. The answer for K1 is, what's that they've given you in the question? Let's see. It's, 1.6 into 10 to the power 6. That is equal to 1. So K2 is also equal to 1.6 into 10 to the power 6. So for this question, K1 and K2 are same. So answer for this question is option B, 1.6 into 10 to the power 6 per second. Did you follow this? Okay. EA is 0. When this is 0, the whole factor becomes what? 0, irrespective of the temperature. Yes or no?
Yes, sir.
Yes. The next question. What is the activation energy for a reaction if its rate doubles? Read the question very carefully. What will be the activation energy for a reaction if its rate doubles when the temperature is raised from 20 degrees to 35 degrees? So they're asking you to calculate the activation energy. The only formula to calculate the activation energy is log K2 by K1 is equal to EA by 2.303 R T2 minus T1 divided by T1, T2. See, the statement clearly says, if the rate doubles, when I say rate doubles, I can write K2 is equal to 2 times K1. K1 is low temperature, rate constant at low temperature. K2 is the rate constant at higher temperature. So when you increase the temperature from 20 to 25 degrees Celsius, the rate constant doubles, they say. So I can write at 20 degrees Celsius. 20 degrees is nothing but how many Kelvin? 20 is 293 Kelvin. At 293 Kelvin, K1 is equal to K1 only at 35 degrees Celsius. 35 degrees Celsius is how many Kelvin? It is 308 Kelvin. K2 will be double the rate, twice K1. You followed this. Its rate doubles, they say, when you increase the temperature from 20 to 35 degrees Celsius. So 2K1. So what is this now? Log K2 is what? 2K1 divided by K1, that is equal to EA by 2.303. R value is 8.314 into T2, what they've given. Higher temperature, it's 308 minus 293 divided by 308 into 293. So on simplification, we'll get the energy of activation EA value. It's very simple. K1 and K1 will get cancelled. So you'll get log 2. Log 2 will be 0.3010. Remember at least log values from 0 to 10, right? 1 to 10. So 0.3010, that will be equal to EA by 2.303 into 8.314 into 308 minus 293 divided by 308 into 293. So that will be, on simplification, we will get EA to be 34673 joules. 34,673 joules. It can be written as 34.673 kilojoules. So the answer for this question will be option A. It's around 34.7. So the closest value is 4.7. Did you follow? Kindly go through this problem. Kindly go through this problem. Did you understand, all the students?
Yes, sir.
Yeah.
Yes, sir.
Please go through this problem. Any clarification you can ask me. Next question. The decomposition of hydrocarbon follows the equation K is equal to 4.5 into 10 to the power 11 per second e to the power minus 28,000 K by T. What will be the value of activation energy? They're asking what will be the value of activation energy. We know that from Arrhenius equation, K is equal to A into e to the power minus EA by RT. Now, what's the given equation? Given equation, K is equal to 4.5 into 10 to the power 11 per second into e to the power minus 28,000 K by T. Now, comparing these two equations, comparing equation 1 and equation 2, comparing equation 1 and 2, we can write, or we get, minus EA by RT is equal to minus 28,000 K by T. We can equate these two. We can equate this with this. When we equate and simplify, what we get is EA will be equal to 28,000 K into R, because T will get cancelled. We know that R value is 8.314. So when you simplify or multiply these things, we get 232.79 kilojoules per mole. Kilojoules per mole. Hence, the answer for this question will be option B. All right. Answer for this question is option B. So officially, we are done with this chapter. Few more questions I want you to learn. I will teach you a few more questions now. If you have any clarification with the chapter theory-based also, you can ask me. Theory-based, you have any questions? Or else we'll solve a few more questions today quickly. Any clarifications?
No, sir.
Others?
No, sir.
No. Hopefully you're following the videos of the previous classes. People who have not attended the regular class. Now, for the people who are absent, I'm taking this 20-30 minutes what I have to work some of the problems, right? So catch up with the problems also. I've given you 2-3 derivations. You should see the derivations also. Rate constant for a zero order reaction, rate constant for a first order reaction, half-life period, all that I've given, derived. So kindly go through those derivations. Only then you can work out the problems. You should know the formula to work out the problems. So give me some time. What happened? This is also not getting finished. All right. The next question we will see. The question is this: 50% of the reaction, 50% of the reaction was completed in 50 minutes. 50% of the reaction was completed in 50 minutes. The reaction was found to complete in 100 minutes. The reaction was found to complete in 100 minutes. What is the order of the reaction? What is the order of reaction? The question is very straightforward. 50% reaction was completed in 50 minutes and the reaction was found to complete in 100 minutes. What is the order of the reaction? So what is given? They say 50% of the reaction, completion of the reaction, 50% of completion in 50 minutes. 100%, see, they say they've not mentioned the percentage. They clearly say the reaction was found to be completed in 100 minutes. That means 100% of the reaction is completed in what? 100 minutes. So the reaction belongs to zero order reaction. Zero order. This reaction belongs to what order? Zero order. Why? For a zero order reaction. For a zero order reaction, we know K is equal to X by T. X is the amount of reactant left. That is 50. What's the time? That's 50. Again, it's 1. And for the next set, it is again X by T. 100% completed in 100 minutes. So again, it is 1. That means zero order reaction is independent of concentration. Since zero order reaction is independent of concentration, now 50% of the reaction is completed in 50 minutes and 100% of the reaction is completed in 100 minutes. All right. The next question we will learn. I have to write. I didn't have time to type the questions more. I hope you followed. See, there is one relation what I gave you. All right. Now the relation is this: half-life period of a reaction. So half-life period of the reaction, T half, is proportional to 1 by a to the power n minus 1. This is half-life period, and n is the order, a is the initial concentration. So for a zero order reaction, T half will be independent of what? Initial concentration. Since the half-life period will be directly proportional to concentration, zero order reaction. So when we say zero order reaction, you just observe here, T half will be proportional to 1 by A to the power 0 minus 1. So what will be T half? T half will be directly proportional to A. So you can see here, 50% completed in 50 minutes, 100% is completed in what, 100 minutes. Since half-life period is directly proportional to the concentration, initial concentration, we call this reaction to be a zero order reaction. Followed with this relation you should know. They can ask you for one more. What is the relation between concentration, order, and half-life period? The relation between half-life period, order, and concentration is T half is inversely proportional to inversely proportional to A to the power n minus 1. The next question, the first order reaction. The first order reaction, rate constant, sorry. The first order rate constant for the decomposition. The first order rate constant for the decomposition of N2O5, nitrogen pentoxide, at a particular temperature. At a particular temperature is 6.2 into 10 to the power minus 4 per second. 6.2 into 10 to the power minus 4 per second. Calculate the half-life period. Calculate the half-life period. It's a direct question. These kind of questions only will be asked in your 12th standard. For a first order reaction, you remember rate constant is equal to 0.693 by T half. We have derived this relation. Or we can write T half is equal to 0.693 by K. They have given rate constant here. Rate constant is 6.2 in 10 to the power minus 4. So it will be 0.693 divided by 6.2 into 10 to the power minus 4. It's a simple simplification. You can take this 10 to the power 4 to the numerator, minus 4 to the numerator, it becomes 10 to the power 4. And on simplification, we will get 1118 seconds. So the half-life period for this particular reaction is 1118 seconds. Follow this, students?
Yes, sir.
Yes. Ajay?
Yes, sir.
The next question. I will write it for a few minutes, so just wait. Next question is this. The half-life period of a first order reaction. These kind of questions are important. Of a first order reaction is 60 minutes. The half-life period of a reaction is 60 minutes. How long will it take for 75% completion of the reaction? They're asking the half-life period of a first order reaction is 60 minutes. How long will it take for 75% completion of the reaction? So this can be worked in two stages. The first stage is to find the rate constant. Since it is first order reaction and we know that K is equal to 0.693 by T half. They have given half-life period, they have given directly 60 minutes. So what will be K? 0.693 by 60. That will be equal to 0.01154 per minute. So rate constant for a particular reaction remains constant throughout the reaction. Whether you measure the reaction at the very initial stage or at the later stage, the rate constant value remains same. So since rate constant is not given, we can find the rate constant by using the data half-life period. Once we have done with the rate constant, the second step of the reaction is we have to find how long will it take for 75% completion of the reaction. So K is equal to 2.303 by T log of A by A minus X. So I can write time required for 75% will be equal to 2.303 by T. K, we can bring K here to the denominator. T, or take it to the left side, log of A by A minus X. That is equal to 2.303. K value we found out here, 0.01154. It will log to the base 10 of. A is initial concentration. Since they have given in terms of percentage, we have to take A to be 100%. So it will be 100 minus 75. So that will be equal to 2.303 divided by 0.01154 log 4. This 100 by 25, it's log 4. Right? So log 4 is 0.6021. Log 4 is 0.6021. I want you to memorize the log values from log 1 to 10. So it will be 2.303 by 0.01154 into 0.6021. On simplification, you will get 120 minutes. So that means the time required for 75% completion of the reaction is 120 minutes. These kind of questions will be asked in your 12th standard. Just go through this question quickly and we will solve a few more questions a little later. See how I work this problem. Students, did you follow this? First, we're supposed to find the rate constants. Once you find the rate constant, then you're supposed to find the time required for 75% completion of the reaction. The next problem. We'll work the next problem. Is there any clarification with these problems, what we're working now?
No, sir, no doubt.
No.
No, sir.
All right, all right. The next question, the rate constant, no, not the rate constant, rate of the first order reaction. The rate of first order reaction is 1.5 into 10 to the power minus 2 mole per liter. See, it is rate, it is not the rate constant. The speed they have given is 1.5 into 10 to the power minus 2 mole per liter per minute. Mole per liter per minute. At 0.5 molar concentration. The concentration is 0.5 molar. Calculate the half-life of the reaction. Calculate the half-life of the reaction. So the rate of the first order reaction is 1.5 into 10 to the power minus 2. And they're asking you to calculate the concentration they've given 0.5, calculate the half-life period. Now, we know that for a reaction, A giving you product, rate of a reaction is directly proportional to concentration of A. This is based on the law of mass action. If you remove the proportionality sign, we have to give a proportionality constant, K. Now you can see they've given you the rate. Rate is 1.5 into 10 to the power minus 2. And we don't know what is K. They have not given K, but they've given you the concentration of the reactant to be 0.5 molar. So if that's the case, what will be K? K will be 1.5 into 10 to the power minus 2 divided by 0.5. So it will be 3 into 10 to the power minus 2. 3 into 10 to the power minus 2 per minute. This is the rate constant, the first part of the topic. But what's that they're asking? It's a first order reaction, they say, and they're asking you to calculate the half-life period. Since they are asking you to calculate the half-life period, we know it's a first order reaction. So K will be equal to 0.693 by K, T half. 0.693 by T half, which is the second one. So, or we can write T half is equal to 0.693 by K. That will be equal to 0.693 by, what is K? We found out K to be 3 into 10 to the power, excuse me, minus 2. If you take 10 to the power minus 2, the numerator, it becomes 10 to the power 2. So we can simplify this, and the final answer, what we get is 23.1 minute. So the half-life period for this reaction is 23.1 minute, meaning 50% of the reaction will be complete in 23.1 minute. So did you understand the different methods of problem we are working? So the different types of problem we are working, I hope that you're following. So one more question will work. Let's see. Students, did you get this problem?
Yes, sir.
Yes, sir.
Okay, wait for a minute. See, you should know the theory part of it, and you should know the different formulas in the chapter. Only few chapters we have numericals in chemistry. And once we start organic chemistry, it is only the reactions. All right, but only in 5 chapters, I believe we have problems in 12th standard. Less than 5 chapters. Oh my God. The next problem. T half of first order reaction is 6.93 minutes. The half-life period of a first order reaction is 6.93 minutes. What is the time? What is the time required for 99.9% completion of the reaction? 99.9% completion of the reaction. So what's that they've given you? They've given you half-life period. T half they've given as 6.93. Now from this we can find the rate constant. We know the rate constant is 0.693 by T half. It will be 0.693 by 6.93. That will be equal to 0.1 per minute. Rate constant is 0.1 per minute. Once the rate constant is found, we can find the second step of the reaction, that is time required for 99.9%. So we can write K is equal to 2.303 by T half log of A by A minus X. We can write T half is not T half. See, sorry, this is T 99.9%. So time required for 99.9% will be equal to 2.303 by K log of A by A minus X. All right, 1 minute. So we know that initial concentrations is 100. So 2.303 by K we found out it to be 0.1 into log of initial concentration is 100. 100 divided by 100 minus 99.9. So it's with a simple simplification. Right? This is what happened. This is 0.230. 2.303 divided by 0.1 is 0.2303. Log of this 100 minus 0.91 is 0.1. So the 100 by 0.1 is log 1000. So you should remember log 1 is 0, log 10 is 1, log 100 is 2, log 1000 is 3. So it will be 0.2303 into 3. That will be equal to that will be, what's the simplification? It will be 9, 0, 9 and 6, 0 point. So this will be the answer for this, and time will be in minutes. They've given you in minutes, na? Here, yeah, they've given in
Yes.
minutes. So this will be also in minutes. Did you follow this?
Yes, sir.
Yeah, any clarification in this chapter, you can ask me. I'm not going to continue this chapter in the next class. The next class will start a new chapter. Not the coordination compounds. Any clarification?
No,
Students? Others? No, no. Ma'am,
Yes,
ma'am,
sir.
stop the class.